If a private jet costs millions and offers an exclusive experience, how can it be that it does not have the same level of safety as a commercial airplane? Intuition pushes us to think that it does because a small and modern aircraft, with luxurious interiors and operated for select clients, seems more controlled and safer than a giant that transports hundreds of passengers every day. Many people associate the private with greater care, with closer attention, even with greater reliability. However, safety does not depend on the price of the aircraft, nor on the luxury of the cabin, nor on the number of seats. It also does not depend on whether the aircraft is large or small, because in aviation, that intuition is misleading. Real safety is built on something much deeper, the architecture of risk. That is, the entire technical, structural, operational, and regulatory system that surrounds the aircraft from the moment it is designed until it is withdrawn from service, and it is precisely within that system where the fundamental difference appears. Commercial aircraft are designed, certified, and operated to move hundreds of people day after day without interruption through thousands of flight hours. They are subject to extremely strict transport regulations, with requirements for redundancy, structural testing, maintenance, and operation that represent the highest level in the aeronautical industry. Private jets, on the other hand, are created for a different mission. Flexibility, access to small airports, personalized operation, less weight, fewer redundant systems, and a highly variable operating environment. That does not make them unsafe by definition, but it does create a different ecosystem. An ecosystem that does not pursue the same standards, nor necessarily needs to, because its function is not the same either. And that is where it becomes interesting. It is not about luxury versus mass transport. It is about understanding why, even when both fly in the same sky, they do not share the same design foundation nor the same levels of safety required by regulation. The root of everything begins with a simple idea. When the mission is different, the design is different as well. If a commercial airplane and a private jet do not pursue the same mission, what structural difference makes it so that they also do not share the same safety standard? To understand this, we must look much earlier than certifications, maintenance, or regulation. We must look at the moment when each one was conceived and the problem it was meant to solve, because that is where the real difference begins. A commercial aircraft exists to move hundreds of people in a constant, predictable, and repetitive way, which is why its operational life is intense, with daily flights, continuous cycles of takeoffs and landings, long routes, strict schedules, and enormous mechanical wear accumulated over a relatively short period. This requirement shapes every design decision, since the structure must be capable of withstanding thousands of hours of annual operation, and the systems must be prepared for multiple redundancy so that everything is robust enough that an isolated failure, as much as possible, does not affect safety or interrupt operations. In other words, a commercial airplane is designed with the premise that the flight must be able to continue even when something stops working. That principle implies that the aircraft can continue flying safely even if a system fails, because it is not an aspiration but a condition integrated into its very structure. A private jet, on the other hand, is born for a completely different mission. Its objective is to offer flexibility, autonomy, and access to small airports, not to support an industrialized operation. It can take off from short runways, operate on irregular routes, land at remote airports, and adapt to the personalized needs of the owner or operator. To achieve that versatility, the design is oriented toward lighter and more efficient solutions, with systems intended for less intensive use and structures adjusted to a different operational profile. In that context, a private jet does not usually accumulate thousands of flight hours per year, nor perform constant cycles week after week, so it is not subjected to the same pattern of repeated loads, nor to the same level of accumulated wear. These differences do not imply that one aircraft is better or worse than the other, but rather reflect that they are not intended for the same purpose. A commercial airplane functions like an industrial machine prepared to operate continuously for long periods, while a private jet is conceived as a vehicle focused on flexibility and availability, not on mass transportation, nor on extreme levels of redundancy. When this divergence is analyzed from structural engineering, the gap becomes even more evident. The fuselage of a commercial airplane is prepared to dissipate the loads associated with repeated pressurization, while its wings are designed to flex across hundreds of thousands of cycles without compromising structural integrity. Its hydraulic, electrical, and control systems include duplications or triplications, and each of these elements responds to safety margins designed so that the aircraft can tolerate foreseeable failures without losing its ability to operate safely. In a private jet, the design remains safe, but it is oriented toward an operation with less repetitive wear. The structure is lighter, redundancy is usually lower because regulations allow it, and the mission also does not require such a high level of fault tolerance. The objective is different: efficiency, availability, and performance in diverse environments. What is important is that these differences are not a matter of style or corporate philosophy. They are supported by aviation regulations. The mission of each aircraft determines the category under which it is certified, and those categories do not require the same things because they are not designed for the same purpose. If the mission is different, the design is different, and if the design is different, the safety will be different as well. At this point, there is something that deserves a closer look. Under what rules is each one certified to guarantee its safety? The difference in safety between a commercial airplane and a private jet does not begin when they take off, nor when they enter maintenance, nor even when they are put into service. It begins earlier, at the moment when they are conceived and certified, and that certification is not the same for both. A commercial airplane is certified under the FAR 25 regulation, or its European equivalent CS 25, a category reserved for transport aircraft that must move large numbers of passengers and cargo, operate thousands of hours per year, and sustain very high levels of structural and operational requirements within civil aviation. FAR 25 requires that the structure be capable of withstanding load margins far above normal operating conditions, and establishes strict criteria to ensure that hydraulic, electrical, navigation, and control systems maintain sufficient redundancy so that a failure does not compromise the flight. The philosophy guiding this approach starts from a very clear premise. The aircraft must be capable of maintaining safe flight even when something stops working, integrating into its design the capacity to tolerate failures without compromising safety. This principle forms one of the pillars upon which modern commercial aviation is built. In addition, FAR 25 imposes rigorous tests that include full evacuations in less than 90 seconds, pressurization tests, fire resistance, bird strike impact tests, structural verification under complex loads, damage tolerance analysis, and demonstrations of operation under demanding weather conditions. These tests are designed to cover a wide range of operational situations and to ensure that the aircraft maintains high levels of safety throughout its service life. On the other hand, many private jets are certified under FAR 23, a framework intended for smaller aircraft within general and executive aviation. It is not a lower regulation, but rather a set of requirements designed to respond to a different mission, in which the demands are adjusted to the weight, the characteristics of the aircraft, and the operational environment in which it is expected to operate. FAR 23 does not require, for example, the same redundancy in hydraulics, avionics, electrical systems, or pressurization systems. Many light jets operate with simpler systems, with fewer redundant channels and with lower load margins because they are not intended to transport hundreds of people nor to operate thousands of hours per year. Nor are they required to demonstrate the same structural resistance to damage or impacts. Their philosophy is usually fail-safe, where a failure requires ending the flight as soon as possible, not necessarily continuing it under normal conditions. The differences become even clearer when physical testing is compared. While a FAR 25 aircraft must undergo load tests that push its structure to 150% of its operational limit, a FAR 23 aircraft is subjected to lower loads consistent with its category, not because it is less safe, but because its mission does not require the same margins. This translates directly into the way both types of aircraft are built. A commercial aircraft incorporates redundant systems because its category requires it, structures capable of resisting long life cycles because its operation demands it, and damage tolerance criteria defined by its certification. A private jet, on the other hand, can be lighter, simpler, and more efficient because the rules under which it is certified recognize that its operating environment is different. But certification only marks the starting point. Once in service, aircraft enter a world of maintenance, operation, and standardization that further expands this difference. If a commercial aircraft is regulated and tested to withstand multiple failures, what difference appears when both enter real operation and maintenance? In daily practice, that difference stops being purely regulatory and begins to be reflected in the way each aircraft is maintained, operated, and integrated into its technical environment. Safety is not defined only in manuals, but in how it is applied day after day within very different operational systems. Commercial airlines operate within a strictly industrialized system. Every flight forms part of a vast chain that includes maintenance technicians, support engineers, operations personnel, inspectors, regulators, and manufacturers. In that environment, behind every aircraft, there are hundreds of professionals working in coordination within a system where maintenance is organized with precision through A, C, and D inspections, defined by flight hours, cycles, and calendar intervals. In this way, everything remains standardized so that the aircraft preserves its integrity even under intensive use. In addition, technical support is structured through global networks that allow airlines to have spare parts warehouses, certified tools, updated technical documentation, and qualified specialists at major airports. As a result, when a discrepancy is detected, action is taken immediately, and in the presence of any relevant anomaly in a system, the operation is stopped according to established procedures because operational safety is part of the system's very functioning. The same occurs in the cockpit. Airline pilots go through simulator training every 6 months with mandatory evaluations of procedures, emergencies, CRM, and decision-making. Standardization is so strict that 2 pilots who have never flown together can operate as if they had done so every day. The human factor is not left to chance. It is regulated, trained, and controlled. In the world of private jets, the reality is very different. There are top-tier corporate operators with extraordinarily high standards, but there are also small companies, individual operators, and even private owners who do not have the same technical structure or the same logistical capacity. Maintenance remains safe, but it is not necessarily industrialized with the same intensity or frequency. Regulations allow this variability because the mission is also different. Private jets fly fewer hours per year in more flexible environments and with irregular operational cycles. But that same flexibility introduces uncertainty. Scheduled maintenance exists, but it may vary depending on budget, availability of spare parts, or the operator's internal criteria. Another key point is spare parts management and technical support. Airlines have immediate access to parts in stock. A private jet operator, on the other hand, may depend directly on the manufacturer to obtain specific components, which implies longer waiting times and, in some cases, more constrained operational decisions. In terms of wear, the difference is not only quantitative but also qualitative. A commercial aircraft accumulates hours and cycles in a systematic way, allowing maintenance teams to anticipate precisely when each component must be inspected thanks to a predictable usage pattern. In a private jet, by contrast, the flight pattern may vary considerably. Short trips on the same day, long periods on the ground, operations at remote airports, and less uniform flight profiles. Added to this scenario is the human factor, which also introduces differences. Airline pilots operate under highly defined, standardized procedures and within complete teams, whereas private aviation may involve smaller crews, a lower level of standardization, and more variable operational environments. A private pilot can be extremely competent, but the context in which they operate is not the same as that of an airline. This is where the gap becomes evident, an industrialized system versus a more flexible one, both safe but not equivalent. And this operational dimension is only part of the picture because when we descend to the level of internal engineering, where redundancy, fault tolerance, and system architecture come into play, an even deeper separation appears. When observing the internal structure of each aircraft, the difference becomes even clearer. It is not about luxury, comfort, or aesthetics, but about how systems are designed to manage failures and absorb loads within defined margins. At this level, safety stops being a matter of perception and is understood as the direct result of design. In a commercial aircraft, redundancy is an essential part of the architecture because regulations require that the aircraft be capable of maintaining a safe flight even when one of its main systems stops functioning. In practice, this is reflected in how hydraulic systems are organized, which are usually distributed across independent circuits, so that if one fails, the others remain operational and maintain control of the aircraft. Even in the presence of additional failures, alternative systems are capable of sustaining the essential functions. The same approach extends to avionics, where a commercial aircraft incorporates several flight computers, multiple navigation systems, redundant sensors, alternative control paths, and cross-protections. Each critical component has a backup, and those backups are evaluated through analyses that determine how the system responds to multiple failures, ensuring that these systems can continue operating safely even when cascading failures occur. In a private jet, the architecture remains safe, but it is oriented toward a different approach in which the primary objective is to land safely in the event of a failure, rather than to continue operating under normal conditions. Many light jets operate with simpler hydraulic configurations, sometimes with 2 circuits or even 1, depending on the model. Therefore, when an anomaly occurs, the usual procedure is to divert and prioritize landing. Similarly, electrical systems and avionics often have more limited levels of redundancy, with fewer backups available because the design responds to a different operational profile. This does not reflect a technical deficiency, but rather a design consistent with their mission as aircraft that fly fewer hours, carry fewer people, and operate in different environments. As a result, FAR 23 regulations do not require the same depth of redundancy as FAR 25, because within their category it is considered sufficient to meet operational objectives. At the structural level, the physical limits also reflect these differences. Commercial aircraft wings are designed to withstand extreme load cycles over hundreds of thousands of hours, and their structures are capable of tolerating repeated pressurization, demanding maneuvers, severe turbulence, and adverse weather conditions. Ultimate load tests push the wing to approximately 150% of its operational limit as a demonstration of the expected structural stress. In the case of private jets, the structural margin remains safe, but its scale is different. The accumulated fatigue is lower due to a smaller number of annual cycles, meaning the structure is not intended to support continuous operation over prolonged periods. Instead, it is designed for more sporadic and flexible flight profiles with less repetitive wear. Beyond engineering, the real conditions in which each aircraft operates also play an important role, from altitudes and routes to airports, flight profiles, and the operational context that each one faces in practice. With these differences in mind, it becomes inevitable to look at what happens when each aircraft faces environments, altitudes, and routes that are not the same either. How does that context influence the way safety is managed? In practice, the operational environment introduces dynamics that go far beyond the design of the aircraft. Because the way flights are planned, operations are supervised, and contingencies are managed directly shapes the level of safety that can be maintained in each type of operation. Commercial aircraft operate within a highly controlled system. Their routes are predefined, optimized, and supervised by control networks that cover virtually the entire planet. A commercial flight takes off knowing exactly which altitude levels it will use, which routes it will cross, which alternate airports are available, and what procedures will apply if any contingency occurs. During cruise, a commercial aircraft usually flies at high altitudes between flight level 350 and flight level 410. At these levels, traffic is regulated and aircraft have enough margin to fly above turbulence and adverse weather phenomena. In addition, these flights take place in supervised airspace, where air traffic controllers guarantee separation, order, and safety along each segment of the route. Private jets operate in a more variable environment, where their main strength is flexibility and the ability to adapt to different scenarios, which at the same time implies facing less predictable situations. These aircraft can use small airports, short runways, remote airfields, and locations with more limited infrastructure. In many cases, approaches are carried out with less technical support available, with simpler guidance systems and fewer ground services compared to major airports. The altitude at which the flight takes place also introduces differences. Although some modern private jets can operate at levels comparable to commercial aviation, many fly at lower altitudes, where weather phenomena have a more direct influence, with a greater presence of icing, more noticeable turbulence, and denser cloud formations. This increases the probability of encountering more demanding atmospheric conditions during the journey. Within this same context, the use of airspace introduces another layer of difference. A private flight may cross regions where control is limited or non-existent, especially outside the main corridors. This implies a greater workload for the crew, more autonomous decision-making, and less external support. A commercial flight, by contrast, rarely takes place in an environment that is not extensively documented and supervised. Added to these conditions are performance limitations, which also influence how each aircraft can respond to demanding scenarios. A commercial aircraft has the power and capability to climb above intense turbulence, manage adverse conditions, or execute maneuvers with wide margins. Many private jets, due to their smaller size and configuration, may operate with tighter margins in situations such as high temperatures, high-altitude airports, short runways, or loads close to maximum limits. Within this same framework, flight planning also reflects these differences. An airline must plan additional fuel according to strict regulations regarding contingencies and alternate airports. A private jet, depending on the operator and the mission, may adjust its planning to the available range or rely on alternates with different levels of infrastructure. This does not imply lower safety, but rather an operational environment with greater variability and less standardization. Taken together, these differences directly influence operational safety because each layer of variability introduces new factors that must be managed. A commercial aircraft is designed and operated to reduce that variability as much as possible through stable routes, optimal altitudes, robust infrastructure, and continuous supervision. A private jet, on the other hand, is conceived to adapt to the unexpected, accepting a more diverse environment that can sometimes be more demanding. After examining design, certification, engineering, operations, and environment, the picture becomes clear. Safety is not an isolated attribute, but the direct consequence of an entire system. Therefore, when we compare commercial aircraft and private jets, we are not comparing machines within the same ecosystem, and that difference ultimately becomes tangible in operational outcomes. Commercial aviation is designed to reduce variability almost to zero. Every decision, every maneuver, every maintenance action, and every procedure is carried out within a standardized framework that is constantly tested and audited. Everything is oriented toward maintaining reliability at extraordinarily high levels. Private jets, by contrast, operate in a much more flexible environment, where that ability to adapt is valuable but also introduces variations associated with operating on shorter runways, remote airfields, less predictable weather conditions, more limited infrastructure, and tighter planning. Crews may work under different levels of standardization, and technical support depends largely on the operator. None of these variables is unsafe by itself, but together they create a more dynamic environment. The difference is not technological, but systemic. A commercial aircraft is backed by companies that manage their fleets with industrial discipline. Hundreds of technicians, global spare parts warehouses, strict manuals, continuous audits, mandatory simulators, deep redundancies, and an extensive network designed so that every flight occurs under the most controlled conditions possible. In private aviation, the reality is heterogeneous. Some corporate operators maintain impressive standards comparable to those of an airline, but many others operate with smaller structures, tighter budgets, and less uniform procedures. As a result, operational quality can be excellent, good, or simply adequate depending on who manages the aircraft. This variability translates into risk levels that are not identical. The mission also plays a role. Commercial aviation transports hundreds of people every day and is designed to ensure the continuation of the flight even when a critical system fails. Private jets, intended to carry a small number of passengers along flexible routes, are not required to support that same level of redundancy. Their philosophy prioritizes a safe landing in the event of any anomaly rather than the continuation of the mission. Neither approach is better. They are different because they respond to different needs. Operational results reflect all of this. Commercial aviation maintains one of the highest levels of safety of any industry on the planet, the product of an ecosystem that functions like a single machine. Private aviation, although also safe, simply does not operate under the same level of standardization, nor does it use the same infrastructure, nor does it carry the same obligation of redundancy. Its risk is not dramatically higher, but it is different because it exists in an environment where variables change more frequently. What matters is understanding that speaking about differences in safety does not mean that a private jet is unsafe. Rather, it means that the way it is built and managed responds to different parameters defined by its mission, its category, its operational environment, and its philosophy of use. When operated within those frameworks, it represents an extraordinarily effective way of flying, even though it does not correspond to the same system or the same experience as commercial aviation. In the end, these differences are not flaws of the system, but part of the very design of aviation itself. Two worlds, two needs, and two engineering philosophies that converge toward the same purpose: sustaining air operations at extraordinarily high levels of safety. And although both achieve it, they do so through different paths, with different tools and within operational frameworks that respond to different logics. Understanding this contrast helps explain why safety does not manifest in exactly the same way in each case, since the systems that sustain each aircraft have been conceived to respond to different operational contexts. From this perspective, every takeoff reveals the result of decades of technical decisions, design trade-offs, and mechanisms created to manage the improbable with quiet precision, reminding us that aviation is not only about machines, but about complex systems working in harmony. To continue discovering how the systems that keep the sky moving are built and operated, subscribe and continue this journey in the upcoming videos.